Yeah. So if questions are saved till the end, saves messing about with the electronics, it'll be fine. So, this evening, very pleased that John Moyle has come to speak to us again with details about the laying of the telegraph to India in the Victorian times, when, to a certain extent, they were wanting to avoid going under sea because it was a bit easy for it to be intercepted. And that sounds fine, but it must have been a horrendous task. So, another one of those examples where they battled on through. So I think we just hand over to John to give us his lecture.
Yep.
Thank you very much.
Thank you. Well, am I switched on? Yes. I thought I'd better start, for those who haven't heard me talk, and putting anybody to sleep lately, about what my background is, because it's a bit strange. I left school with 4 O-levels, and I'm sure everybody here knows what an O-level is, but at the 20th attempt, I got 4, and I went in to do an apprenticeship in electronics with Mullards and part of the Philips group in the era of valves and slide rules. And I progressed at the end of that to the medical division of Philips, dealing with X-ray equipment. Strangely, I couldn't stand the sight of blood. I used to pass out at the thought of it when I left school. But having been forced on me working in the medical electronics division, I was in and out of hospital, and I was seeing that blood was under control. Things changed a bit because Philips wanted to put me into a management stream, and so I revolted, bolted, and went and read medicine. Philips were very good, actually, because while I was having university vacations, they actually gave me my job and a car back during vacations, which was extremely good of them. So I ended up, after qualifying, as an anaesthetist and running in an intensive care unit, or several actually, over the course of 24 years. That is me. I shouldn't have been an anaesthetist because I can't do crosswords. But that's just to tell you actually that we don't read newspapers, and my wife is one of these in the background here. And nor did we use colour gas, but it serves a point showing that slide. To get back to what I'm meant to be talking about, just a few things to remember before I go on with the rest of it, is that before the Suez Canal was open, it took ships from going from the UK to India 3 to 4 and sometimes 5 months going around South Africa. After the Suez Canal was opened in 1869, it was much reduced to 2 to 3 months. During the period we're interested in, the London to Paris cable and landline was fully functional by 1851. And I'll mention in a moment the difference that was used in those days between cable and landline. And the other significant date, which really stirred things up, was the end of the mutiny in India in 1858, when the government really wanted to speed things up as far as communication was concerned. If you want to look at anything to do with politics, diplomacy, finance, or biographies, then this is probably the most up-to-date and best textbook to look at. I don't know if you can read the title there. I'm not going to read his name out. It's something to do... Sharma was his first name, I get that bit, but he's Finnish, actually. And he's written a series of books which are about the politics, diplomacy, finance, and some biographies of the cable system around the world. And they're very good books. But there's one thing missing out of them. There's no technology in it at all. He was a historian. There are very few technical books. written even now, which have a lot of technical detail into them rather than just the politics and the diplomacy. Because with a lot of the history of technology, unfortunately, people don't have a first degree in an engineering or scientific subject. A lot of them were doing ordinary history and then got interested in it. I'm afraid that isn't really quite good enough. But strange as it may seem, I know absolutely nothing about politics, diplomacy, finance. I do the occasional biography. All I know about history comes out of these two books, which is surprising, really, because I managed to get a PhD in history of technology and also a fellowship of the Royal Historical Society. I bet they haven't heard this lecture and they'll probably run my name off. To get back to the subject I'm meant to be talking about, to do with telegraphs in India. This is an interesting chap, Shaughnessy. Perhaps I read it from that one up there rather than break my neck. He was a doctor who trained in Edinburgh in medicine and in forensic chemistry. And right back in that era, in the 1830s, he described and actually tested the use of IV and infusions of electrolytes in treatment of cholera. Because cholera, most people die because they can't keep the fluids on board. He didn't experiment on human beings, he experimented on dogs. Nobody let him near otherwise, even though what he found and published was still being used today. He went to India in 1833. I can't really work out why he went to India, but he went there on with a medical background and was interested in botanical pharmacology, drugs from plants and things, and also toxins. And he also worked out or tested in human beings the medical uses of cannabis. But also, he was a real polymath in it. He was interested in electricity and all sorts of electric motors, and in telegraphy. And in fact, by 1855, he had managed to sort out, that's meant to be a picture of India, a complete network of landline telegraphy, which was just ready to be connected to another country, basically. It was a fully working system by 1855. Now, the landline telegraphy is strictly telegraphy not involving the sea. And it's very straightforward. You have a straight key, a straight-looking Morse key, and electric wire and a sounder. Now, most people think that when you're sending telegraphy, it's da 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 da, etc. It was worse than that in those days. There were no bleeps or anything. A dot would be coming out of that device at the top there. This one here, and a dash would be, so it's how they managed to get up to speeds of up to 80 words a minute, goodness only knows. The sounder was all they had. There weren't any earphones. Later on, he has this contraption called the Morse inker here, which a drawer underneath had a paper slip rolled in there and a clockwork mechanism pulled the paper strip, or they call it a slip for some reason, past, here's the equivalent of that here, pulling a pen down on the strip and actually marking out on here the dots and the dashes. But that came later on. The cheap and easy way was just with the sounder. So the difference between landline and submarine cable becomes important. The landline was very simple. It was either copper, or in the UK, where it was fairly short distances, they used iron as a wire because people stole the copper. The insulation was air or porcelain. There was no electrical capacity on the line at all, up to, believe it or not, 80 words a minute, which some of the Americans could manage. Crude, simple electrics and no theory. One of the bits of test gear they used was their own tongue. On the climb up the pole, touch a tongue on it, and if you get a shock in the tongue, it's probably working. This compares, or does not compare, with the submarine cable, where it was always a copper conductor. There was an enormous electrical capacity because it was like an elongated Leyden jar. In other words, there was a single conductor insulator, and the seawater acted as the earth return. It was just like a huge electrical capacitor. Enormous electrical capacity, which I'll show you in a moment. The signals were very weak, and they were very slurred, and got worse and worse the further and further the cable was. And up to about the late 1890s, it was around a maximum speed of 40 to 20 words a minute. And they really had to work out the science of it, and the name to look out for is Lord Kelvin, William Thomson, who also made a lot of money out of it. You had to use very sensitive instruments, both for reception of the signals coming through and also in the repair of the system if it went wrong at all. And the big problem was to find an insulator suitable for use of the cables under the sea, or under the river for that matter. And basically it was the worst up here and the best up here, going through like that. And this was copied out of a journal, out of a book from 1886. But it wasn't until gutta percha was available that they really could make cables which could go under the sea. The gutta percha comes from a tree called the Paloquium gutta tree. That's what a diagram at the time would have looked like in a botanical book. Gutta percha is interesting in that it's similar to rubber and can be thought of as a sort of isomer of rubber, but it's got different electrical properties. It's hard, plastic and hardish, up to 100 degrees Fahrenheit. Above 150 degrees Fahrenheit, it becomes quite plastic. The electrical insulating properties are enormous, and in fact, it gets a better insulator the deeper you take it in the sea with this external pressure. And it actually really does get better. Extremely low coefficient of thermal expansion and contraction, and a very, very good insulator. Unfortunately, it only comes from a small area in the world, as you can see here in that sort of area in the Far East. I could read out the places, but I won't, because you can see them from where you are. The trouble was, in theory, that you could actually get the gutta percha out of a tree in a similar way that you could get rubber, India rubber, out of a tree bark. And this is one of the pictures that's always used, and I'm not sure how they got away with it in view of this young lady here. But unfortunately, they didn't do it that way. They chopped the trees down and took the bark off and get the gutta percha off that way. And they used 300 trees per nautical mile to get enough gutta percha to insulate over the sea. under the sea. The cable, soon after the initial attempts of putting cables under the sea from the UK to Europe, very soon the cables ended up looking like this and stayed looking like this until about the 1930s, which is when polyethylene and synthetic insulators became available. Basically, there's a single copper conductor, it's a twisted single copper conductor there. Gutta percha is there, and round it is brass or copper tape all the way along, and that is to stop the Tornado worm eating the gutta percha, which they had a delightful time. It damaged their teeth on the brass tape. And you must have heard the expression, something is copper-bottomed. Well, the reason the expression came from is because lots of wooden ships were being eaten by the Tornado beetles and would suddenly sink. And they found that if they put a thin layer of copper or brass sheeting over the hull underwater, the ships were no longer eaten by the Tornado beetle. So the brass tape protects against that. It's not part of the electrical circuit. It happens to be there, but it's not. Then there's jute and a tarry sort of substance around it. Then there's metal, these are steel wires round in spiral round the cable with tape and servings of insulating material, usually involving tar and a sort of hemp material around it. So the cable was like that really for 80 years or so. But they made different thicknesses of the cable. The central bit here is the same in all of the diameters of the cables, but the armouring is massive until you get down to deep sea level. This would be known as a shore end of the piece of cable, and this would be on the continental shelf, and as soon as you got off the continental shelf, there would be much less armouring, because there are no, the cables would just lie on the ground, on the sea floor. There are no currents once you're off the continental shelf. So near the continental shelf, they had to have this enormous armouring, not only to protect the cable from being rubbed on rocks and coral and things, but also to try and protect it against anchors and fishing things, either hooks or nets or any other such thing. Now, I mentioned that it's got a high capacity, electrical capacity. It's equivalent. This is like drawn by what Lord Kelvin did an electrical equivalent circuit of it. That cable that I've just shown you would be about 10 ohms per nautical mile and about 0.35 microfarads per nautical mile in electrical capacity because of the core and the seawater. And here at the bottom here, passing a current, switching a current on and switching it off, and this represents what happens because of the capacity. It slowly comes up, and when we switch off, it slowly comes down exponentially. For 100 around 100 nautical miles, in other words, really between the UK and the continent, in various that peak here would be about 5 milliseconds it would take to get up there. 2,000 nautical miles, it would take 2 seconds before it reached the peak, and that would be equivalent to the North Atlantic. And the longest that was used was Pacific, and that would be 6 seconds for this signal to show up at the far end of it. Now Now, the two types of keys we used, two types of code we used. Landline code was just the same as ordinary Morse. In other words, the dot and the space and the dash would be 3 times as long as the dot, and that would be a letter space there. This did not work on these long C cables, so they used what's called cable code, and instead of the difference in time between a dot and a dash, in inverted commas, the dot will be positive signal. The dash would be a negative signal. It would be both the same in time, and likewise all along here. And the reason for that is so that you could actually distinguish what the signals were. So if you were looking at the letter L, which is dot, dash, dot, dot, so we've got one dot and a dash and a dot and a dot. So the C, the A one is the longest cable, and you can see there's hardly any difference between 2 dots and 1 dot. If you look at the figure 5, which is 5 dots in a row, it would be like this. The longest cable would be like so, and the shortest cable would be much more obvious. But you can see the amount of difference there was between the two. Now, how do you think that they read that? Well, that was a bit more difficult to understand, really. They used a cable key, which was like 2 Morse keys adjacent to each other. One was for the equivalent of dots in inverted commas, and the other dashes in inverted commas. In other words, one will give you a positive signal, and the other will give you a negative signal. And at the far end, ignore this for the moment because that came a bit later on, but at the far end there was a thing called the mirror speaking galvanometer, which is what Lord Kelvin called it. Here we have a light source pointing in the direction of this here, which was a galvanometer, a mirror galvanometer, and the signal will be moving across here very slowly, depending on how far it was. The most difficult thing to deal with was the fact that there was no side tone. I don't know if anybody here is a radio amateur, but a side tone is you hear your own Morse signal. Well, you can't do that because A, there's no noise, B, you'd have to have the equivalent of the same signal length or cable length. And so it required complete darkness and 2 operators concentrating very hard. One of them were working out whether it was a dot or a dash, depending which direction it moved and how, and it might have gone like that and a little wiggle at the top and back down again, depending on how many dots there were or whatever. And the other person was writing down what the person reading it said. They had to concentrate very hard, and they worked for about 20 minutes at a time and then swapped over to be able to do it without going insane. So if we get now to the actual cable and landline routes, there were basically 4 via the Red Sea, via the Persian Gulf. Siemens had a Russian network going north of Persia, and the 4th one, which we ended up with, and we started with actually, was from Cornwall to Bombay in the Mediterranean via the Red Sea. But initially, the Red Sea cable, they wanted to get it to. They thought that they could get it to work easily, and it was not. It was in 1859 that they first one of the things was that you think it's easy because you'd only got a little bit of sea to go across here. And the signal hence went to Paris, and then from then on afterwards. This map is from 1874, and I'll show you in a minute why it's very difficult to find maps of the time. And I've marked in red what they already had going through here. They could get to around here, and they just thought, okay, we'll come down here, which is actually 1,000 nautical miles down through the Suez Canal and the Red Sea. But this proved to be completely disastrous. And fortunately, they started there first before they made lots of other errors. But initially, there was a lot of urgency from the British government after the Indian Mutiny. They really wanted to get things a bit faster than 3 or 4 months. So the UK government set a 50-year unconditional guarantee of 4.5% on the whole 800,000 capital for the Red Sea circuit. And the company they signed up with was Newell & Co., one of the bigger cable makers. But it never worked. It was never successfully completed. The cable design was completely unsuitable and inadequate, and poor surveying. There was the coral at the bottom of the sea in the Red Sea, the seabed ravines and mountains. It was just hopeless. It kept snapping. And one of the worst things was that part of the contract said that they could keep any extra cable that they didn't use. So what they did was it went over these mountains and ravines, lacking care of laying, was putting it mildly. They put it taut, so taut that there were catenaries hanging between the various obstructions in the sea, mainly because it was supposedly because it hadn't been properly surveyed, which of course would have saved the government a lot of money, because in the end, because of the legalities of it, the guarantee, it didn't work, and the government had to honour the guarantee for £36,000 per annum, and that was a hell of a lot of money getting on for 200 years ago. So what happened next was there had been a number of cable failures. The only ones that were really successful were the short distance ones. But as soon as they tried laying across the Atlantic, a failure, 1856, short-lived, and then the Red Sea disaster. And the Board of Trade set up a committee of inquiry, which ran for about 18 months, to see if it was even worthwhile carrying on laying long-distance sea cables. And in fact, they said it was, because they did get the right people to be on the committee. And what they'd found was that it was just too shoddily done and no accuracy of anything, because it had never been done before. And so they tightened up all the things. For example, the copper core, previous to this, to 1850, nobody was making copper wire for its electrical uses. It was all done for making jewellery, and nobody understood anything. The people who made copper wire didn't understand what the electricians were talking about. So the British Association for the Advancement of Science formulated electrical standards as well. And as soon as they tightened up on all this accuracy and whatever, things became more successful. Notably the Atlantic cable and everything else beyond that. Unfortunately, I made that slide before I knew I was going to give this lecture. So the next step after the complete failure of the Red Sea cable, the initial Red Sea cable, this chap called Patrick Stewart, he was brilliant in the army and in the British Army of India as an engineer. But unfortunately, and he became Director General of the Indo-European Telegraph. Sadly, he didn't last very long. He was young man. He died at 33, which was a great loss to what he was doing. So he was involved in the second cable, and both these cables started from the London area and came across this one. The second one came across this way down the Persian Gulf instead of this route, and along the sea there to Khartoum. To Karachi. There were several things about that particular cable. It was built by the Brits, owned by the Turks, and it was not very successful because where the landline was involved, it went not necessarily in straight lines to wherever you wanted it to go, but it went from bit town to town to town. And the signals involved, usually the wiggles in the line were due to where the railways were, because the railway lines ideal place to put poles up and telegraph lines. But it wasn't a brilliant success. Especially around here, the Bosphorus. Yeah, I found Bosphorus spelt in umpteen different ways, and anyway, it's a bit of land that had to be crossed here in near Istanbul, Constantinople, Istanbul, and it didn't work. They weren't very good at laying lines in the sea in that particular area, and they had 3 cable failures before it worked. After some years, it worked. So for 2 or 3 years, the signals came at a landline here and had to be sent by boat. As signals in envelopes rather than electrically across the Bosphorus, Straits of Bosphorus here. So it was not a particularly successful system. So the next attempt was the Siemens Russian network over the north of Persia and over the north of the Black Sea. And one of the reasons for it being laid, its third attempt, was to avoid the Ottoman Empire here, who was sometimes friendly and sometimes not friendly. This cable and a lot of the other cables are mentioned in this lovely book, but don't buy it. Telegraph and Travel by Frederick John Goldsmith. It was written at the time. It's good. It's very technical, but the person who scanned it, it was published at the time. It was a contemporary tome. The person who scanned it was obviously on minimum wage because they didn't unfold the maps. So it's absolutely useless. It actually costs about £40. It's a lovely bound book, but absolutely useless because all the maps are folded, like so. And even include that very good map You can see the Black Sea up there. It looks much better actually when you look at it with a magnifying glass. And you might wonder where I got that from. Well, I'll tell you that the book was out of print and is out of copyright because the author has been dead for over 100 years. And there's a copy of the book, the original copy, original edition in the Porthcurno Museum. And I've scanned it, the whole book, with the maps, all the maps. And I've actually sent you a copy, so if you do get the book, it's better to buy it as a PDF on a CD-ROM, which you can buy it from the museum at Porthcurno, which I'll mention later on. But all the maps, I've scanned them all properly, and they're all bound properly. So it's a lovely book to have, but it's absolutely useless unless you have the maps. Likewise, this was a book which has been copied, been scanned and copied as being a very valuable, useful scientific tome of the right era, but exactly the same. The book, they didn't unfold the maps, so it's pretty useless actually. Anyway, laying the cable over these rocky mountains and things was not that easy, as you can see from here. Some of the stretches were actually 1 kilometre long of landline wire. You can see the size of against this horses here. It was very difficult to land to actually lay cable on until you got down to the really flat bits. But as you can see, that's pretty terrible. One of the problems was that they were using poplar tree wood soaked in copper sulfate in the hopes that it would stop the termites eating it for the poles that they needed to put up. And not only that, the wooden poles, they needed to dig a 4-foot deep hole in whatever ground there was to make the pole stand up and withstand the winter winds and the cable, weight of the cable. Also, they found that people were using the little white insulators, which they had no idea what they were. These people out in the, I can't think of a suitable PC word for them, really. They used them as target practice. Great, lovely white thing, bang. So Siemens produced an iron post instead. And there were two main things about it. One is you could have a different height. This was the bit that was in the ground. And this could be different lengths to see what was necessary in the local surroundings. The difference was that it only needed to be 2 foot deep, because here there's an iron plate, so it withstood the wind and whatever. And the other thing they did was the wild men and their bosses, or the sheikhs or whatever they were, they paid them to protect the cables and the poles that were put up. So, so that was the route that they took, going up above the Black Sea, avoiding the Ottoman Empire. Came around here, down like that, and along like so. This bit here from the Persian Gulf was involved. They actually put the cable on old sailing boats and towed them along the cable unwinding from the sort of sailing barge. But because they needed to be able to control the situation so they wouldn't be rammed by this enormous barge full of umpteen tons of cable, they needed a way to signal between the ships, the tugs that were pulling them, which were Indian Navy, did the pulling. They needed a way of signalling to the people on the barge that they got to slow down, and that they were slowing down or they were changing course or whatever. But they were too far away to do it with flags, so it was done with flashing lights, signalling, and it's thought to be the first time that Aldis lamps were used at sea, and it was 5 to get along here to Karachi. It took 5 of these barges, one after the other, when they had to. The biggest trouble was trying to connect the cable from one the barge to the next, but it was reasonably successful and worked up to there. So then that was the Siemens cable, cable plus landline, and it worked fairly successfully. But soon after, in 1870, the decent seagoing cable all the way from the UK to Bombay. One of the things that had happened so far was that every time you needed to go through a station to improve the signal, to act as a repeater, it had to be received and retransmitted. And it was done by people who weren't necessarily fluent in the English language. And as I said, in some parts, the cable went through landline stations where there was not only 3 different languages, but 3 different alphabets. So the ultimate was to do a cable that was all the way by the sea. And by 1870, we got the manufacturing sorted, the surveying sorted, and they had good cables now right across the Mediterranean. Not just across the Mediterranean, but on bits that we could control. So it now went from Land's End, or near Land's End, at Porthcurno, all the way down to Gibraltar. There were several cables that also went to Lisbon and Vigo, but the most important one going to India came to here, to Gibraltar, to Malta, and then down the Suez Canal, down the Red Sea, out the way it was meant to happen in the first place. But instead of going up to Karachi, it went up to Bombay. That is about 1,400 nautical miles. That's 1,700 more nautical miles. And so instead of having dozens of repeater stations, which were manually operated, it was just Porthcurno, Gibraltar, Malta, Suez, down to here, and then out to there. And not only that, but there was also an improvement in... so that system worked very well because all the recommendations of the committee had been activated. But not only that, also it was not just this method, but a thing called the siphon recorder. The problem with using this mechanism, as I said, it drove you mad. You're doing it in the dark and 2 people and all the rest of it. Very easy to make a mistake. This was invented in 1867, 68 by Lord Thompson. He made an awful lot of money out of this, and then an even greater amount of money out of this because he patented them all. And the siphon recorder was a similar principle to the Morse ink that was used on landlines. This is one that's at the museum at Porthcurno. I'll show you roughly how it works. Here's paper slip coming along through here, over here down to here. This here is called the mouse motor because it looks like a thing where you exercise a mouse on the top, and it generated electricity, static electricity, for which reason I'll point out in a moment with a better picture. But this whole thing was about that tall, about that wide. And how it worked was this. There was a large permanent magnet placed in it. And here is a galvanometer coil suspended on a thread, and two little weights here to try and to keep it central. The signal comes in from the sea, usually via a capacitor for reasons which we could talk about later on, if you wanted to. The signal comes in through that way, and out that way to anything else that needed to be connected. Now, what happened was that this, with the signal coming in, the signal we're talking about is between 1 and 5 milliamps. And this is 50 years before, or a long time before, even thermionic valves. So the signal will come along here, and this would wiggle in the strong magnetic field, depending on the signal coming in here. Now, the thing that you didn't want to happen was you didn't want a lot of friction on the pen or whatever. So what we have here then is this little pot here contains ink. And the mouse motor up here generates a static electricity which comes down, there's an insulator there, into the ink. Now, across here, this is the axis of a little glass capillary tube, which is in the ink there, and comes down here to the paper trace. But it's not actually touching the paper, because if it did, that's too much friction for it to cope with it with only 1 milliamp coming through. But what you have here is static electricity coming down here and is drawn through the plate behind the ink, behind the paper slip. So the static electricity draws the ink, and it comes out across to the paper here and comes out that way. The mouse motor also has a belt which drives the paper being pulled through. But if you can see what roughly that looks like. Sorry? First inkjet printer. It was exactly the first inkjet printer. And it looked like, the results look like this. So if you can see, even then it's quite difficult, but you've got a paper trace of it so you can study it more carefully. As you can see, an A would be a dot and a dash. But of course they're not dots and dashes, they're two different patterns. And a B is dash and 3 dots. And it's got these little dotted lines because in the tropical areas, the plate behind the paper, they made it vibrate slightly to stop it getting stuck because if the ink got the chance to dry out. But as you can see, with a bit of practice, you could read practically anything coming through there. And instead of being London, the signals all came from or to Porthcurno. Initially, when it was just going to Paris and that route, then it was quite short from Kent area across to Cherbourg or whatever. Then with the long distance cables, they moved to Falmouth because it's further out, an easier route to going down to Gibraltar and whatever. But the problem there was its support, and therefore the cables were forever being damaged. So they moved to this deserted place, which is the most beautiful beach if anybody's been there. If you have been there, this bit here is where the Minack Theatre is, the outdoor theatre. And there's a cable hut here. Stormy weather, you can actually still see cables. They come up every so often. People saw bits off and nick them because none of them are being used anymore. But at one stage, there were 20-something cables actually working at Porthcurno. And it was the largest cable station in the world. There's the cable station there. Now, this is now my car. There. I had an Audi TT once. But I'm too old to drive it and too old to get in and out of it now. So, and the Minack Theatre would be up here. The sea would be down here. And the cables went up here into that huge, very, very solid building, which now, which opened in 1870 when they started putting the main cables in from the continent and from the rest of the world. But the station actually only closed in 1970, and within a few years it was reopened as a museum, which is fantastic. This is very up to date because it's just changed its name to this museum. It's called P.K. Porthcurno Museum, which is a hell of a mouthful because everybody used to know it as Porthcurno Telegraph Museum. But I can't say much for that against it because I'm speaking for them now. Are there things that are interesting here? If you've heard about me talking at other lectures, there was a tunnel there, 100 metres U-shaped tunnel, dug into the cliff in 1939 because the station was in operation throughout the Second World War and to protect all the instrumentation from bombs and things. So, that is how things were up until 1870, and from then on, since then they put in lots of duplicate cables, and now, of course, all the cables are fibre optic and not copper. Any questions? I'll try and answer. Oh, some hand up behind you.
Just a second. I'll just give you the microphone because I was going to say, please try and get a microphone before asking a question because even if we can hear you in the room, people at home and on the recording things may not. So.
Hello, Victor Selwood. I'm just a visitor. Can I take slight issue with your description of it as a museum from 1970? Because I actually attended there as a college for a week in 1991. But other than that, very much enjoyed the lecture. Thank you.
Thank you. It's if we go back to the school bit that was down here, I think, in this sort of area, if I'm right in. Not that it really matters. That's the main thing is they couldn't knock that thing down because the walls are about this thick.
Actually, quite an interesting question. So, obviously, the cables are coming in.
Yeah.
But how are the communications then going through into the UK, through to London, through to government, through to wherever else they're going? I've never actually known that.
They were, in that era, they would be read and sent by ordinary landline telegraphy, which was, it was at the peak of its use at that time. They had occasions when things got cut off because they used to have real snow in those days. One occasion, the cable station was shut off for about 2 weeks. We couldn't get to it, but so climate change has changed a bit since then.
Amazing amount of detail. There's a couple of things. The first one was when they were laying the cables, were they overland, were they underground, or were they overhead all the time?
Mainly overhead.
Right. With those poles, whatever.
Yes.
Yeah.
In this country, they were with poles.
Yeah.
There's a bit of underground cabling done in major cities to get through major cities, but again, as soon as they buried cables, they had the electrical capacity problem that it slowed it down.
Right. The other thing was, at what length of cable could they lay? Say, for instance, in the sea, on a boat, there's only so much you can get on a coil. How much did they lay at any one sort of coil's worth, as it were?
Well, the first really successful Atlantic cable was all in one. The first couple were laid in 2 lengths, and they tried to join the middle, and it never really worked.
Oh, right.
But then they got hold of the Great Eastern, which was a huge ship that nobody really wanted. It was a huge liner, really, an absolutely vast thing. But it ended up its days as a cable ship because it would hold enough cable coiled up in a tank that they put in it that it could get across the Atlantic in one go.
So they'd actually manufacture a cable, one piece that went from all the way across to America? That's amazing.
Well, it is. We were the world leaders. The Brits were. All the world's cables in those time were made in along the banks of around Greenwich in that sort of area. People like Newell and the Gutta Percha Company and can't remember. There's a well-known cable company that not only made them, but it went and laid them as well.
Right.
The thing that I found quite strange was that historians, you think that they dug everything out of everywhere, but they hadn't. They hadn't looked. My PhD was about the maintenance of cables in the Victorian era.
Right.
And all the history books were saying, even some reputable ones, were saying that once the cable was laid and you got rid of the faults during its laying, it would last about 70 years and then be replaced. Right. It's absolute rubbish because they just didn't look in the places you look at. At the museum at Porthcurno, there's all the cable and wireless. Because the Eastern Telegraph Company, which was the biggest thing in the world, eventually ended up as being cable and wireless. But all their minute books are there, board minute books, and nobody looked at them before I went down there ferreting around. And fortunately, John Pender, who was a cotton magnate, who poured an awful lot into the cable world. He insisted, he was on the board of the Eastern Telegraph Company, he insisted that every monthly meeting, where his repair ships were and what they were doing. And nobody looked at it. And it turns out that cables were disastrously, people thought they did last for, and it's still in all the textbooks, because they were written by people who didn't know where to look. They were people who were not engineers. And I had a whale of a time.
Brilliant. So when do they stop using these?
When do they stop using it?
Yeah, the cables.
The cables basically they stopped using gutta percha in the 1930s, and then nothing much changed until fibre optics came along, and now it's all fibre optic, no copper cables at all.
So they're still laying cables now?
Oh, yeah. I mean, everybody knows of the... I've got a lovely diagram I draw of the optical communication initially, which was flags and flashing lights and this, that and the other. Then you come around to copper, which includes landlines and submarine cables. Then it moves round to satellites. And then it moves round back up to the top again, optical, where it's all fibre optic. And now the satellites, all they're doing is, apart from navigation, is they're communicating things that are moving, like planes, ships, people who can afford a sat phone. And now everything else goes by fibre optic. And you can tell this by, for example, when my wife used to spend hours on the phone to her sister in Canada, and there's a big delay because it's going via a satellite. It doesn't anymore. You can't hear the delay because it's a fraction of what it was, because it's all going by fibre optic cable, and not satellite.
The things like WhatsApp and do they operate through cable then? I talked to my son in America, and it's instant.
Yeah. That's fibre optic.
Oh, I see. Which is the speed of light, presumably.
Yeah.
Well, thanks very much. Really interesting.
That's okay.
My friend here's got a question.
You described some of the practical problems about the land route with people shooting the insulators. How on earth did they keep the whole route maintained?
Very.
How did they know where the faults were?
Well, finding the fault was fairly easy because you just with the landline ones, you can see where the damage is. You can actually measure it. Nowadays, you can measure it by sending a pulse down and seeing how long it takes to reflect back from the break. But that's very, very modern. The problem was keeping the cables, the landlines, from being damaged. And what they did was they paid sheikhs or whatever. I can't think of any nice way to refer to them, or any PC way of referring to these gentlemen, paying them to spy on who's damaging the cables.
Hello again. Can I declare an interest? I work for Siemens, so I was very impressed to see that Siemens had got their name against a cable, and I wondered why that was, given I think Siemens is 180 years old, so we're probably 20 years old at the time that cable was going in.
Yeah.
So just seems very unusual for a manufacturer, as it would have been, and fairly new startup at that time.
But there were several bits of Siemens. There was Siemens in the UK. There were brothers. There were Siemens in the UK, and there was Siemens in Germany. Because I thought, hello, what are the Germans getting involved in? But it was English Siemens that were doing it, because we were streets ahead of the rest of the world up until almost the whole of the 19th century in cable work. We even laid the first cables across the Pacific. But yeah, there's more than one bit of Siemens.
Yeah, but it was the fact that the cable is actually titled the Siemens cables.
Yeah, well, on the old maps it was put as Siemens cables. That's why I've said it was Siemens cables.
And that referred to Siemens in the UK?
Yeah.
Okay, because we don't tell our German cousins very often, but Siemens was actually established in the UK before Germany. They don't like that for some reason.
No.
A second question as well. All of this above ground cable is going to be prone to lightning strikes and perhaps also even sunspot activity, which can affect power lines and so on. Were there protections against that, or that was just part of... Okay.
When it was landline, you just made sure you weren't too close when the lightning struck you. But with the undersea cables, there were all sorts of things that could muck it up. One lightning strike at each end, one end or the other. And also the magnetic field changes with time. It changes anyway. And all sorts of things like that could muck it up. And even the difference between magnetism day and night would muck it up, for which reason they, at each end, or certainly at the receiving end, there was a capacitor to level out all sorts of spikes that were coming along. And also there were also earth currents that came along, because the magnetism at one end of the cable might be different from the magnetism at the other. At any one time, it could change. So, and there's a mountain of literature about earth currents, which are currents generated by the changing magnetic field, or the difference in magnetic field at the two ends of a long cable.
One comment I'd quite like to make is I was following a story a year or two ago about the voyage of HMS Pearl, who was sent newly built from Britain round. It actually, interestingly, went through the channel and didn't go around Cape Horn. It went, because it had a supplementary steam engine, although it wouldn't wash it. Yeah. Anyway, it was sent across off South America on the Pacific coast, across to Hong Kong when one of the Opium Wars brewed up. And while it was in Hong Kong in 1858, it got orders to go to Calcutta to help suppress the Indian Mutiny. And I've always been intrigued as to how they got orders to it in Hong Kong. Yeah. Say report to Calcutta,
yeah,
and pick up some troops on the way while you're going, because even to get the news back from India in the first place to say the mutiny's broken out,
yeah,
let alone.
But it must have been landlines to do it.
Yes,
because there's land all the way into Hong Kong.
Yes, and the other story, which I think I sent you an email link to when it initiated this, was one of my great grandfathers. Something worked for Parry and Company in Madras. I think we're supposed to call it Chennai now, aren't we, or something? And was there when the Telegraph first got through to Madras, but they were complaining about the garbled messages by the time they'd been written down and retransmitted 25 times by people who
didn't even speak English.
Yes,
yeah,
and,
that was the
they used to have to sit over these messages and stare at them and say, I wonder if that's such and such a word.
But you mentioned the ships. The other thing that the main historians had completely missed is the number of cable ships, real cable ships. There was a book full of them that some gentleman, I'm afraid he's died, Czech called Haig, wrote. And, there's one cable ship for each cable in the world that was being laid. Yeah. And what are these historians, surely they saw this book. It's a lovely bound, hard book. Yeah. What are all these cable ships doing? Well, we're out repairing cables. The failure rate per annum was for every annum, there was a cable failure within 500 nautical miles of cable that was laid. So what happened was that a lot of the cables, when they took them up to the end, they were just patchwork of cables that have been repaired.
I mean, if you look at the map of the fibre optic cables and overlay it over a historical map of the telegraph cables, they match very closely.
Yes, yeah.
I remember about 20 years or more ago, the company I worked for had opened some call centres in India to try and do things cheaper, a bit cheaper. I think. And one day we got a note round the office saying that due to a failure of the SAFE, the safe cable, that communication with Chennai was somewhat limited. And the SAFE is the South Africa and Far East cable that loops all the way down the west coast of Africa, round Cape, across the Indian Ocean to India.
Yeah.
And some ship had dragged its anchor or something and damaged it, and they were having to send it down through the Red Sea or something like that.
But there's a lot of damage done by things, earthquakes that we know nothing about, that happen under the sea. And there are lots of them. And you think that maps, ocean maps now are accurate. They're very inaccurate. Because another thing that happens is that if you have an eruption one side of an ocean, then for some reason it'll trigger a landslide the other side, maybe 1,000 miles away, which will break the cable. And it still does.
For anybody at home watching on Zoom, if you've got any questions, can you use the chat function to ask it? I don't know if we've got any so far, have we? No, nothing at the moment, but we'll give it just a few seconds just in case anybody wants to raise anything. Anybody else got any questions or comments here?
You mentioned the rate of failure of undersea cables. I just wonder how on earth, if you knew there was a failure within a section of the cable, how did you know exactly where the cable was to start? Dredging for it, and presumably all the various cables that there wasn't just one cable going on a particular route. Was there not the risk of pulling up the wrong cable when you're looking for the failed one?
Yeah, a couple of questions, couple of answers there. One is, when a cable failed, they would measure at each end what they could pick up from measuring the resistance at each end. Okay, and you should be able to calculate where the fault was. And the way they did this was when they were laying the cable, every so often, if they did have to lay another piece of cable, they would measure the resistance at both ends, at the sea end and at the land end, and write it down on a chart, the laying chart. And that chart stays with that cable forever. It's gone now, but for the full length of the time that the cable was working. And what happens is you can calculate, looking at the resistance figures on the chart, with great difficulty, but it is possible for them to calculate roughly how far it was along the cable where the cable was damaged. And they can do that from both ends. And when they get nearer this point, they pull up the cable. Their navigation skills were absolutely amazing, considering they hadn't got radar, satellites and the works. They could pick up the cable and they would cut it and measure the resistances both directions and compare them with the chart, and then know whether the fault was one side or the other. And then they rejoin them. And the way they rejoin them was incredibly skillful. And then they move along to where they thought it was, and maybe have to do it again. And quite often, for example, there was one of the longest cable stretches which went from Portugal to Madeira down to Recife in Brazil, had a break. That was 1,700 miles. I'll look at that in a minute. It was 1,700 miles, and it was about 1,000 nautical miles along. And they got measurements that differed from the two ends. And it turned out that it had been a landslide, had broken the cable in two places. And they found it within 4 nautical miles at the end of it, and by grappling it and putting in a loop to grapple the other end. Incredible, really, when you think about it.
But how would you find the cable if the cable was running along there?
They grappled. When they thought they were near it, they would grapple across it. And the important thing was that they didn't leave cables stretched. And short cables, there was 10% slack left around. Long cables, which were very deep, 20% of slack around, so that you could haul it up, grapple it and haul it up without damaging anything any further.
So have they got very accurate maps there then of where the cable was running?
Yeah, there were very accurate maps because the laying companies actually made the maps. The maps are the ocean charts. There's navigation charts and there's piloted charts. The navigation charts were almost all blank because they weren't necessary. The only people who want to know anything about them, the depths, were the cable people and people who were driving submarines and things. The only bit they want to know is about the cable, about the shelf, the continental shelves, which are near the land, and that's where you get the decent quality, or supposedly decent quality charts. But the bits in the middle were actually where they've been surveyed by the cable companies and plotted them on a chart with the depths and things. It was, the trouble was that on a long cable, you probably only do it every 50 miles, and you could quite easily miss a ravine or a mountain. It was easy when we got sonar.
Anyway, we've got one question that's come in, I think, from the Zoom watchers.
Just to qualify, did the messages
come ashore to be repeated at Gibraltar, Suez, yes, Aden, etc.?
Yes, they were cable stations at each place. So between the UK and Bombay, I think it's around 6 cable stations where they were actually, but they were all staffed by Brits, by people who were paid by the Eastern Cable Company. The Eastern Telegraph Company was one of the biggest ones, and what they often did was they laid a cable, a small company, and so they'd lay the cable with the name of that area. And when they could see that it had made some money, then they'd swallow the company and they all became part of the Eastern Telegraph Company.
Much like where the railway systems were.
Yeah.
At what sort of time could they not have designed some basic circuitry to have created automatic repeaters, a bit like you do get in fibre optics?
Yeah, that came around the 1920s, 1930s. They did make it, but it wasn't. The very high power one was about in the 1930s, again by the Eastern Telegraph Company. There were a couple of types. The very potent one does all sorts of jiggery to get the signal to come out the same, and I can't understand it even time when I read it. Earlier on, with slightly where the gap wasn't quite so big, they had got certain ways of amplifying them. In about 1900, there was a thing called the drum relay. What this was a galvanometer affecting a contact on a little arm, like so, but so that it didn't rub and produce friction. What it was, there was a drum going round and round and round, that way, if the needle was this way. And it was divided into several parts. And because it was going round, the friction from the needle, or whatever you want to call it, was reduced, rather than if it was a stationary thing trying to move. So the drum went around and around and around, and the signals came off that. So there were 6 or 7 different devices like that. Such ingenuity that they had before thermionics came along. The true repeater station, which was totally automatic, contains loads and loads of valves and things. But that's probably why I limited my research to the beginning of the First World War, because that came later on. And I keep trying to understand how the repeater system worked.
I think the secret was trying to get it into a small enough box to go over the ship's stern.
Oh, they were always on land. With those sort of cables, they were always on land. The repeaters they did make, which about that diameter and sort of that longish, with valves, but they still had to. They still went wrong. But sorry.
Yes, there's a question up
Oh.
on there. Back in my subsea days, the umbilical cables were contra-helical wire armoured. These were multi-cored, electrical and hydraulic. Did I detect correctly that your single core cable escaped with a single armour layer?
No, they had more than one. The land ends, shore ends as they were called, had 2 completely separate layers of steel or iron wire as a protection. And it only when it got down to the deeper part off the continental shelf, where there was no currents, did they end up with a smaller, much lighter armouring. But the shore ends were always very heavy. I did bring, last time I talked about this here, I did bring a piece of cable with me, but I forgot it and left it here. Got it back a month later. But it was about, the shore end was about that diameter.
Anything else?
Well, thank you very much. It's
Well, it's all.
obviously, from the discussion, it sparked off a lot of interest and a lot of concern. So thank you very much, John. That's very, very good. So thank you.